about the winner and the representation, graphical representation of signals, and how the winner gain relates to this representation. What is theta, the angle between two different signals, which means how they correlate to each other, and how do we define this angle. Okay, so let's see an example to get some intuition behind it. So suppose that we have this kind of signal. Okay, so this is the variance of the signal in the Fourier transform domain, which means that this is actually the spectrum of the signal. Okay, so suppose that the spectrum of the signal is constant for frequencies smaller than quarter, and then 0 otherwise. Okay, so it looks like this. So the spectrum of the desired signal as a function of f, this is the spectrum from minus half to half, okay, because this is the Nyquist frequency. So this is the range. So it goes like this. This is the spectrum of the desired signal, which means that it contains also in the low frequencies. We don't have for the desired signal high frequencies. And suppose that the noise, the spectrum of the noise, which is the variance of V for each frequency, the spectrum of the noise looks like this. Okay, so it's better. This is like normalization, and it goes like this. This is the spectrum of the noise. And here is better. Okay, so this should be a straight line. Okay, like this. Okay, so any filter that you will choose, meanwhile we talked about the Wiener filter, but actually any filter, its objective is to reduce the signal distortion, the desired signal distortion, and to suppress as much as possible noise. So in this high frequency range, see, like in this range, of course, we can cancel the noise completely, obviously, because we don't have desired signal in this frequency range. In this range, what will be the gain? So if I try to plot the gain for all frequency, okay, so it will be here. Okay, so the gain here, of course it will be 0, because we don't have desired signal here. What will happen here in this area? How does it look? Look like this, how does it look? Okay, so we need, for the Wiener gain, if we try the Wiener gain, or any gain actually, it means that when the signal to noise ratio is high, the gain will be higher, and when the input SNR is low, the gain will be lower. Any gain, okay? And the Wiener gain, actually, we know that it looks like input SNR divided by 1 plus input SNR, because we obtained this. But actually, any gain, when the input SNR is high, it will be higher. So at this point, for 0, you see the SNR is lower, and it increases when we come here. Okay? So it can be something like that. Okay? So I don't want to show exactly the structure, but probably it will look like this. You see this number, and so it can go up and then go to 0. And of course it will be symmetric. Okay? Because here it will be lower, and then it goes up, and then here it will jump to 0. Any gain, and specifically the Wiener gain also looks like that. But if we want to find the exact expression, what we need to find is the input SNR, which is the ratio between the spectra, okay, like this divided by this, and then to use it as input SNR and to put into this expression. Okay? So this will be the input SNR, the ratio between the variance of x and the variance of v, and then we have mathematical expression like this. And if we take, this is the narrow band input SNR. If we take the broadband input SNR, so it's the integral of the total integral of the variance of x, total spectrum, and the total spectrum integral over the spectrum of v. And for this example, we get alpha divided by beta. And then we have this expression for the Wiener filter. You see that it's 0 in this range, high frequency range, because we don't have desired signal. How does it look? So if we plot the gain in SNR for using the Wiener gain as a function of the input SNR, so the gain in SNR decreases. First, when the input SNR increases, the noise reduction decreases. This is always true. You see, because when the input SNR increases, we have less noise to deal with. So the noise reduction decreases, and then the gain in SNR also decreases. The MSE also decreases because we have less distortion. We reduce less noise, so we have less distortion and less distortion and less mean squared error. So these plots make sense. The trend makes sense. The exact plot depends on which filter we use. Okay. Let's see another example. Instead of the first example, let's talk about another example, that sinusoidal signal, see, like this. And suppose that we measure this signal on a certain interval, which means that we have only capital T samples of this signal. The amplitude is fixed, the frequency is fixed, the phase is random between 0 and 2 pi, and we measure just T samples, capital T, of samples of the signal. And suppose that we have additive white Gaussian noise. And this is more practical because we use, in the time domain, we used a fixed length filter so we can move it in real time, so on. But here, if we work in the frequency domain, we cannot do Fourier transform on infinite length of the signal. We need to restrict the length what we measure. So suppose that we measure a certain length signal. How do we deal with that? Okay, so this is the time domain signal. Here in the first example, we specified the spectrum of each signal. Okay, so the spectrum of the desired signal, the spectrum of the noise. Here, because it's given in the time domain, we need to move to the Fourier transform and find the spectra, okay, of these signals. So what do you think? What is the spectra of white Gaussian noise? What? Constant, okay. Let's see if it's constant, okay? What about this? It's a sine trend. It's a sine. Sine or cosine, that doesn't really matter. If you have a single frequency, what is the spectra? Of a pulse. Okay. Okay. So I agree with you if the signals are with infinite extension, okay, from minus infinity to plus infinity. But because we are looking for truncation, specific length of measurement, so it's not exactly, okay? So if we have window of length capital T, a certain window of measurement, we multiply this window with either a pulse or a constant. So in the time in the frequency domain, if we have in the time domain multiplication, what do we have in the frequency domain? Sinc, which is the convolution between the Fourier transform of each. Okay? So because we have a certain measurement, so we have a sinc. We will see that it's not exactly a sinc because we have on a certain length, so it's a periodic sinc, which is the Dirichlet function. Okay? And then we have a periodic sinc, Dirichlet function, convolution with a spike or with a constant. So let's see. So these small details are important when you solve problems or you deal with problems. So let's move on. Okay. So first, regarding the spectrum of the signal. Okay, so let's talk about the Fourier transform of our signal, xt. So xt is a sine function like this, and we compute the Fourier transform at a certain length of the signal from 0 to t minus 1. So we have capital T samples of the signal. So if we compute it, we get this. This is the Fourier transform, which is exactly the Dirichlet function, Dirichlet kernel, sine tx divided by sine x, which is similar to the sinc, but it's not sinc. It's periodic sinc. Okay? You see? So this is the Dirichlet kernel convolved with the impulse. Okay? So we get this. This is the Fourier transform of the desired signal. Okay. And this is, so the variance, you see, so the variance of the desired signal will look like this, or the spectrum of the desired signal. So you see you have, this is similar to sinc, but it's not sinc, it's like the periodic sinc, which is centered around F0. And another one centered, this is centered around F0, and this is centered around minus F0. Because you have the two frequencies, the positive and the negative. Okay? This is the spectrum. So it's not just two pulses, it's around each pulse we have the Dirichlet kernel. And the Fourier transform of the noise, of the white Gaussian noise, but it's with a certain length of the signal. So it becomes, if we compute the Fourier transform like this, so it's a constant. Okay, it's a constant with the variance, but this constant you multiply with t, the length, the number of signals, the number of samples. So the input SNR is the ratio between the variance of x and the variance of v. So we get this expression, which is multiplication with a certain constant of the Dirichlet that is centered around minus F0 and plus F0. So this is the input SNR, and we can use the input SNR to compute the Wiener gain. So what we see is that this Dirichlet kernel it goes to 0 very quickly around the pulse. Okay? So this is the broadband input SNR if we want to compute it. It's just the integral of phi of the variance of x divided by the integral of variance of v, and we can compute the broadband input SNR. And if we talk about an example where the amplitude of the sine is 0.5, f0 is 0.1, and we measure 500 samples of the signal, of the noisy signal. So here we see the gain in SNR, the MSE, the noise reduction factor, and the desired signal reduction factor as a function of the input SNR, using that is obtained with the Wiener gain. Okay? So we see the trend. Of course, the noise reduction decreases, the gain decreases, the MSE decreases, and the distortion decreases as we increase the input SNR. But if you remember, we did something similar in the time domain using a filter of 30 samples. Here, when we go to the Fourier transform, we work with the whole signal of measurement of 500 samples. So we can obtain a better performance. Okay, so here we see a realization of the signal. So this is a realization of the noisy signal. So you see these two spikes. So it looks like spikes, but it's not exactly spikes. It's a Dirichlet kernel around each point. So if we take, this is the magnitude of the spectrum of the noisy measurement. So you see we have this this is for the positive frequencies, this is for the negative frequencies. So we see that we have a frequency that is high, this is the desired signal, around 0.1, frequency 0.1. So after we apply the Wiener filter, we get this. This is the spectrum of the estimated signal. This is the signal in the time domain, the inverse Fourier transform of y, and this is the signal, the estimated signal in the time domain. Okay, so we see here nice thing. If you compare it to the Wiener filter that is obtained in the time domain, here it's much better. Why? Because we used 500 samples, and we used the Fourier transform over the 500 samples, and we applied the Wiener gain in the Fourier transform. So it looks much better if we compare it to the time domain. Over there we worked with short length filters of 30 samples. Here it's much longer. But beyond that, I want to discuss with you what kind of information did we use to obtain this estimate, these gains. So we assume that for each frequency, we know accurately the input SNR. It's not obvious to know the input SNR. Usually we need to estimate that. Okay? But once we know accurately the input SNR, you see, we were able to clean the noisy measurement, and we could obtain a quite clean, you know, it's not perfect, of course, but it's very nice looking spectrum of the desired signal if we know the input SNR. But it's not easy to obtain input SNR. So when we'll work with the short time Fourier transform for speech enhancement, when we continue and we reach speech enhancement, you will see, so you can record your voice, you get you add some noise, even white Gaussian noise, and then to know for each frequency and each time bin in the STFT to know the signal to noise ratio, it's problematic. Of course, if you know the clean signal, you can you know the input SNR for each time frequency bin in the STFT domain. But of course, you don't know the clean signal. So even if the noise is stationary and white, like white Gaussian noise, even then, because the desired signal is non-stationary, it's very difficult to know for each time frequency bin the input signal to noise ratio. Okay? So this will be the example that you will work on for speech enhancement. It will give you some practical challenges, how to do signal enhancement, even for single channel. Okay? But here, so, okay, so let's continue with the trade-off gain. So the trade-off gain, also similar to the time domain, but instead of working with the MSE, we define a different problem. We try to minimize the MSE-based signal distortion, okay, JD, because we know the MSE is composed of two components. One is related to the signal distortion, and one is dependent on the residual noise. And we try to minimize the distortion, MSE, subject to the noise-related MSE will be Aleph, where Aleph is a parameter, multiplied with the variance of V. So to solve this problem, we can use Lagrange multiplier and choose this Lagrange multiplier such that the constraint is satisfied. Or we can keep the Lagrange multiplier constant and play with that. We can keep it a constant for all frequency, or we can change for each frequency this Lagrange multiplier, whatever you like, so that this constraint or requirement will be satisfied. And so here we get, you see, so it's equivalent to multiplying the variance of V with the parameter mu. So if mu is larger than 1, it means that we give more weight to the variance of the noise. It means that if mu is larger than 1 in that frequency, okay, so in that frequency we will reduce more noise. But if we reduce more noise, the distortion also will increase. It comes together. Suppressing more noise increases also the distortion. So we have this expression, and vice versa. So for each frequency, by controlling this parameter mu, we can control the trade-off between noise reduction and signal distortion. Okay, in some frequencies, if we want to reduce more noise, we can increase the signal distortion. If in some frequencies we want to reduce less noise, we can change mu for each frequency. And we can change, of course, mu such that the constraint will be satisfied. So we get, you see, in the time domain, for examples we had to do it numerically, here we can get this expression. So we can obtain mu such that the constraint and the residual noise-based MSE, that it will be satisfied. So we have nice relation between mu and Aleph. Okay? So if we want, actually if we want that this narrow band constraint will be satisfied, it means that the gain should be square root of aleph. So it's very obvious. We can also talk about the magnitude squared coherence function between x and f plus. So when we talked about the Wiener gain, we talked about what is the coherence function between x and y. Here we define something different. We define x plus square root of mu v. And then we define the coherence between both of them. And then we can write the trade-off filter as the magnitude squared of this coherence function. And it makes sense, right? So if I plot it, if I give a representation like this, okay, just like what we did, this is with the Wiener. With the trade-off, what did we do? We tried to minimize the mean squared error with the parameter mu. Okay, so instead of minimizing the j that looks like jd plus jn, what did we do? We put here a weight, mu, right? And then we give, if mu is larger than 1, we give more weight to this part. And then we are able to reduce more noise if mu is larger than 1. So you see, this is mean squared error, which is equivalent as multiplying the noise with the square root of mu, increasing the weight. So if we give a graphical representation of this problem compared to the Wiener problem, so we have x, and here we have square root of mu multiplied with v. Okay, you see why? Because here we multiple mu with something which is square root, mean squared error, which is, we have here something which is related to v squared, mu multiplied with v squared. So it's similar like multiplying v with the square root of mu. So we can define here theta with the parameter mu. So this is the, so this will be x plus square root of mu v, and this is theta mu, which is the angle between these two. Just like what we see here, okay? So this is the angle. I will define the angle immediately, but we look for the magnitude squared coherence between x and x plus square root of mu v. And this is actually the gain of the trade-off filter. And we can define this angle, okay? So this angle, so we define it like this. So this is the coherence between x and x plus mu, square root of mu v, plus j, the coherence between v and x plus square root of. You see, instead of y, we write x plus square root of v, because this is the new, we want to give more weight to the noise. And this will be defined as theta mu. And we see that we can define, we can obtain the trade-off gain as cosine square of theta, just like we did with the Wiener gain. So it's just like extension from the Wiener, where mu equals to 1, to trade-off. The parameter mu controls the trade-off between noise reduction and signal distortion. And we have specific expressions similar. You see, instead of theta, that was for the Wiener gain, we have theta mu. That is for the trade-off. See, it's very, very nice relation. Let's see what is the effect of mu on the performance measures. So here we see, we go to the previous example, and then we apply the trade-off filter. So we have the noise. Let's see about the noise reduction, okay? So the noise reductions, we have for different mu. Here, the red one is mu equals to half. The blue is mu equals to 1. Mu equals to 1, which is like the Wiener. Yeah? The green is mu equals to 2. And then this one, mu equals to 5. So you see, when we increase for a given input SNR, when we increase mu, we give more weight to the noise, like here or here. We give more noise when mu is, we give more weight to the noise error. So the noise reduction will increase because the trade-off filter would like to reduce this part. But then it will come at the expense of higher distortion. So you see, when the noise reduction increases, also the distortion index also increases. See, for a given input SNR. The gain, what happens with the gain? Okay? So the gain, when we increase mu, the gain decreases. Because when the gain decreases, it means that we suppress more noise for each frequency. If we suppress more noise, it also may affect, or it affects the distortion. And this is theta. So when mu, you see, when mu increases, this part increases, so theta increases, theta mu. So if we plot theta mu as a function of the input SNR, so for a given input SNR, when we increase mu, you see, when we increase mu, theta mu increases, just like this graphical representation. And we have the property that for any mu, no matter any positive mu, not only for mu equals to 1, any positive mu, we have the output SNR, which is at least as the input SNR. So the trade-off filter, just like we know in the time domain, the trade-off filter improves, or at least does not degrade, the signal-to-noise ratio for any mu. And the proof is just like for mu equals to 1, well, for the Wiener, but you change, you multiply. Okay, so you can follow the proof. Any questions on this example? And the trade-off and the Wiener. So we learned about the Wiener and the trade-off. Let's see. Yeah, question? Okay. Somebody ask a question? I hear something? Oh, okay, sorry. Okay. So let's see another example. Let's go to the first example that we saw at the beginning with the spectrum of the signal, this art signal, this, and the spectrum of the noise, like this. So suppose that we have this example, which we said example number 1. Let's see plots of the gain in SNR using the trade-off filter, the MSE, the noise reduction factor, and the desired signal reduction factor for different mu. Mu equals to half, 1, 2, and 5. Okay, red is half, blue is like the winner, mu equals to 1. This mu equals to 2 and 5. So we see that for this example also, for a given input SNR, okay. So for a given input SNR, when we increase mu, the noise reduction increases. Similar to what we saw before. And then the gain in SNR increases because we increase the noise reduction. The distortion, we pay for that. So the distortion also increases. What happens with the mean squared error? So the mean squared error is minimal when mu equals to 1. Okay? So because when mu equals to 1, we have the Wiener filter, or the Wiener gain. And it's minimal when mu equals to 1. So you see the blue line is the lower line. The trade-off tries to trade off between noise reduction and distortion. But for the MSE, we obtain optimal solution with mu equals to 1. Now let's talk about parametric Wiener gain. So parametric Wiener gain, we can, now that we define, actually we can do even more than that, but this is, I want to give you some intuition and the things that you can do. Sometimes you find solutions, and then you can add parameters for the solutions and see how these parameters give you different relations between existing solutions as specific examples, and also it can add more flexibility in the solution. So here I can define something new. I can define a gain function that looks like this. And I can define it with two different parameters, mu1 and mu2, like this. And then you can ask, okay, why should I give it like this? And theta is just like what we defined here. This is theta. Okay? How did I define theta? Such that cosine theta equals to coherence between x and y. I can define theta. So I can write h, a new h, new gain, with parameters mu1 and mu2. That looks like that, 1 minus sine to the power of mu1, and all of that to the power of mu2. Now, if I choose mu1 and mu2 equal to 2 and 1, if I put here 2 and put 1, what do we get? The Wiener gain. This is exactly the Wiener gain, because the Wiener gain, we wrote it as cosine square theta, which equals to 1 minus sine square theta. So specific parameters of mu1 and mu2, like 2 and 1, will give us the Wiener gain. But not only that, I can get, now I can, in the previous example, the trade-off gain, I saw what is the effect of mu, what is the effect of mu on the performance, and the gain in SNR, and the noise reduction factor, and the desired signal, the reduction factor, and the mean squared error, and so on. Okay? So I show what is the effect of mu on different performance measures. And you agree that if I increase mu, I increase the weight, and then I get more noise reduction at the account of increasing the signal distortion. Now, if I give you an expression like that, so I can ask you, what is the effect of changing mu1 and mu2? And also I can ask you, okay, what are the range of values that I can use for mu1 and mu2. So I can plot two-dimensional map of the values of mu1 and mu2 and find maybe specific examples, specific gains that are known in the literature for specific examples of values of mu1 and mu2, but also try to find what is the effect of these parameters. So this is a very conventional way in signal processing to work with parametric functions and ask about what is the effect of these parameters. With a trade-off, it's very simple. We have only one parameter. And then this parameter, we understood what is the effect of this parameter. Also here, we can put two parameters like this and ask ourselves, what is the effect of these two parameters? But first, if I give you certain specific cases, so if I plot, if I see a map as a function of mu1 and mu2, so if mu1 equals to 2, let's say here 1, here 2, here 1, here 2. So if mu1 equals to 2 and mu2 equals to 1, here, this is the Wiener. Okay, so we have the Wiener gain, okay? Wiener gain. Let's see about other special cases. So we can choose mu1 equals to 2 and mu2 equals to half here. And this is also something that is well known in the literature, and it's called power subtraction. Okay, this one is power subtraction. Let's call it. And if we choose mu1 equals to 1 and mu2 equals to 1, both equal to 1, here we have magnitude subtraction. Okay, so the power subtraction method and magnitude subtraction factor method and Wiener gain, they are all known in the literature. And we see that they are special cases of the parametric gain that it can be obtained with other values of mu1. And then we can ask ourselves, okay, we know about these three, but what happens? I can choose different values, and I can modify these parameters to obtain something, which is also a nice method to obtain different trade-offs. But here, if we just compare these three, it is well known that magnitude subtraction is more aggressive than the Wiener gain. And the Wiener gain is more aggressive than the power subtraction, which means that in terms of noise reduction, magnitude subtraction reduces more noise than this one, and Wiener more noise than the power subtraction. And so the one, this reduces more noise than this, and this more noise than this. But in terms of the distortion also, this distort more the desired signal because it reduces more noise than the Wiener, and the Wiener reduces more noise than the power subtraction, but also has more distortion. So we can play with that, but you can also choose other parameters, and you can get these relations between them. Okay, so the magnitude the noise reduction that is obtained with the magnitude subtraction is higher than the Wiener and higher than the power. But the distortion, you see, is also when the noise reduction is higher, the distortion is also higher. And the nice thing is that you can choose different parameters, but also you can find what is power subtraction, how is it obtained, how do you obtain the power subtraction. Okay, so let me, I don't know how much time do I have, so I can talk shortly. Okay, so I want to give you some information. Why do we call power subtraction this method? What does it mean? And what is magnitude subtraction also? Why do we call it magnitude subtraction? What is this method? Okay, the Wiener gain, we know. We obtained it by minimizing the mean squared error. Okay, power subtraction, this method is also well known in the literature. It means that we take this model and we say that we can write that the variance of y, you see, it equals to the variance of x plus variance of b. Right? Because this is x and v are uncorrelated. Okay. So we can write it like this, that the magnitude squared of x, which is not the variance, it's not the variance, we can say it's equal approximately to phi y minus phi v. Okay? This is one step. So this is power subtraction. Power subtraction, because it's the power, the variance, the power of y, f. Okay, this is the first step. Let's move on. Because we want to find an estimate. Now, instead of writing this, we don't know the variance of y. We need to estimate it. So we will write xf hat magnitude squared. This will be an estimate. It will be phi, the variance of y, f, which we don't know. So I put it here, hat, because we estimate it based on the measurement, minus phi v hat, which we also estimate for measurement. But instead of just putting this difference, because these are estimates, so we don't know if this will be larger, necessarily larger than this. And this should be positive number. So we must add something, so we put here max between this and 0. Do you agree? I can do that. Actually, in signal processing, I can do anything that I want. But I need to check that it works. Okay? You can do anything. If it works, very nice. If it doesn't work, change it, modify it until something works. But I can try different things. Okay, how do I continue? So I can say, you know what? An estimate of this can be like this. So I will write xf hat equals to max yf magnitude squared minus phi v f hat. Okay? This is easy. I have the measurements. Regarding the noise variance, in many cases, many applications, it's also easy to find it because the noise is stationary. And maybe during intervals where we don't have the signal, we can estimate the variance of the noise. Okay? So this is called power subtraction. What is the gain? The gain for this power subtraction. How do we find the gain? I remind you, the gain looks like that. Okay, this is Z. Is HF multiplied with YF. So the gain is this ratio. So if I divide it by Y, okay, and if I assume that it's positive, it looks like that. But I don't have to assume that it's positive. Here it's squared missing. Okay? You need to correct me if there is some mistake. Okay? So you have the squared here. So what I can do, how do I find it? Okay? So I need x, not the magnitude. So I can take x hat like this, square root of this, okay, this is the magnitude. Now I will take the phase of y, because I estimate the magnitude, and I take the phase of y, so it looks like this. Okay, so I got an estimate of x, the desired signal. So if I divide it by y, if I divide all this by y, I get the gain for the power subtraction method. So this is called power subtraction method. Something similar, it can be done also with magnitude subtraction. Similar approach. The noise variance is still what? Unknown. I said, but it's easy to estimate. Why? It's easy to estimate because many times you have the noise is stationary, and even if it's not stationary, maybe during pauses of the signal, and you know when you don't have the signal, so you can just take the variance and average it by using the noisy measurement, because the noisy measurement will contain only noise. So you can average that. Okay? So this is, in many times, easy to estimate. That's why I get it here. Of course, I cannot write V magnitude squared because I don't know it. So I take the average. Okay? So this is power subtraction, and it's well known, and we can write it similar like this with the parameters, but we can use other parameters. So if I go to the example here, I see that if we take the example, one of the examples before, and I compare this, the red, blue, and green, H. So I tell you, one of them is the Wiener, one of them the magnitude, and one of them the power. So you immediately know which one is which, because the magnitude subtraction is more aggressive, which means that H is lower. So the red one is magnitude subtraction. The blue is in between, which is the Wiener. And the green is the power subtraction gain as a function of the input SNR. So the noise reduction, when the gain is lower, you see you have higher noise reduction. More noise is reduced. But then the distortion index, the distortion is also higher. The more noise that you suppress, so with the magnitude subtraction, you reduce more noise, but also the distortion is the highest. The Wiener is in between, and the power subtraction reduces less noise, but it also involves less distortion of the desired signal. Questions? Okay. No, it went back. Assignment number 2. Okay. So today I'll give you assignment, and tomorrow we'll talk about speech enhancement in the short-time Fourier transform. Okay, so try to do this assignment even today because it's simpler. Tomorrow it will not be mandatory, just for people who are interested to do some practical examples with speech enhancement. I think it's nice. Okay, so this assignment. So first you have a few theoretical problems. I think that just to work with simple examples like this. So you have spectrum of a desired signal like this, and spectrum of noise like this, which is white additive noise. And then I ask you to compute a few things: the input SNR, the Wiener gain. It's quite simple. And then to compute the broadband input SNR, and to compute the optimal Wiener gain. And show that the MST looks like this. I think here. Okay. I think it's quite easy. Okay, so it should take for you a few minutes, I think. Okay, it's quite easy. The second thing is with the MATLAB code. So I want you to generate figure 9 in example 4, what we saw before, and play with the parameters or change, do something else, and try to understand what you do. Okay, figure number 9 is this one. What we just compared, the magnitude subtraction, the power subtraction, and the Wiener. So take maybe other signals, maybe change the type of noise, do something, take a look at the code, the MATLAB code, play with it. Okay, and then here we have a table that compares this Wiener, the trade-off, and the parametric Wiener gain, how it looks like. So you can play. For example, number 9, instead of the magnitude subtraction, you can take different values of mu1 and mu2 to see what is their effect. How do they, either you can change the signals to see the effect of different values of mu1 and mu2, not only these 3 examples. Okay, whatever you like. So this is the second assignment. And tomorrow we will talk about non-stationary signals, so about implementation with the short-time Fourier transform domain. Okay? Questions? Okay. Thank you.